Power factor is a crucial concept in electrical engineering and power systems. It describes the relationship between real power, which performs useful work, and apparent power, which is the product of voltage and current. Understanding power factor is essential for efficient energy utilization and minimizing losses in electrical grids. The power factor is defined as the cosine of the angle between the voltage and current waveforms in an alternating current circuit. Mathematically, power factor equals real power divided by apparent power. Its value ranges from 0 to 1. A power factor of 1, also known as unity power factor, indicates that the voltage and current are perfectly in phase, and all the power supplied is being used effectively. A power factor less than 1 means that the voltage and current are out of phase, and some of the power is being wasted. There are 3 types of power factor: leading, lagging, and unity. A leading power factor occurs when the current leads the voltage, which typically happens in circuits with capacitive loads. A lagging power factor occurs when the current lags the voltage, which is common in circuits with inductive loads like motors and transformers. A unity power factor, as mentioned, is when the voltage and current are in phase. Different types of loads significantly impact the power factor. Inductive loads, such as motors and transformers, cause the current to lag the voltage, resulting in a lagging power factor. Capacitive loads, such as capacitors used in power factor correction, cause the current to lead the voltage, resulting in a leading power factor. Resistive loads, such as heaters and incandescent lights, have a power factor close to unity because the voltage and current are nearly in phase. Low power factor has several detrimental consequences. Firstly, it increases the current flowing through the electrical system for a given amount of real power. This increased current leads to higher resistive losses in the conductors, resulting in wasted energy and increased heating. Secondly, low power factor reduces the capacity of the electrical system as more current is needed to deliver the same amount of real power. This can overload transformers, generators, and transmission lines. Thirdly, low power factor can cause voltage drops in the system, leading to poor voltage regulation and potential equipment malfunction. Methods to mitigate low power factor primarily involve power factor correction. Power factor correction aims to bring the power factor closer to unity, thereby reducing the wasted energy and improving the efficiency of the electrical system. The most common method of power factor correction is to use capacitors to compensate for the reactive power drawn by inductive loads. Capacitors generate reactive power that is opposite in phase to the reactive power drawn by inductive loads, effectively cancelling out the reactive power and improving the power factor. To calculate the power factor of a circuit, one needs to know the voltage, current, and impedance values. The power factor can be calculated using the formula power factor equals real power divided by apparent power. Real power can be calculated as voltage times current times the cosine of the angle between voltage and current. Apparent power is simply voltage times current. The angle between voltage and current can be determined from the impedance of the circuit. Impedance is the total opposition to current flow in an alternating current circuit and is a complex quantity with both resistance and reactance components. Reactance is the opposition to current flow due to inductance or capacitance. Once the impedance is known, the angle between voltage and current can be calculated using trigonometric functions. Designing a power factor correction circuit involves selecting appropriate capacitors or inductors to compensate for the reactive power drawn by the load. The size of the capacitor or inductor depends on the amount of reactive power that needs to be compensated for. This can be calculated based on the load's power factor and the desired power factor after correction. The goal is to select a capacitor or inductor that will bring the power factor as close to unity as possible. Selecting appropriate capacitors or inductors for power factor correction involves considering several factors. Firstly, the voltage rating of the capacitor or inductor must be sufficient to withstand the voltage of the electrical system. Secondly, the capacitance or inductance value must be chosen to provide the appropriate amount of reactive power compensation. Thirdly, the capacitor or inductor must be able to handle the current flowing through it without overheating. Fourthly, the cost, size, and efficiency of the capacitor or inductor must be considered. Optimizing the power factor of a system involves balancing several competing factors including cost, efficiency, and space constraints. Increasing the power factor improves the efficiency of the electrical system and reduces energy losses. However, the cost of implementing power factor correction can be significant, especially for large industrial facilities. The optimal power factor is typically a compromise between achieving a high level of efficiency and minimizing the cost of power factor correction. Space constraints can also be a factor, as capacitors and inductors can take up a significant amount of space, particularly in densely packed electrical rooms. Power factor correction is important in industrial, commercial, and residential settings. In industrial facilities, large inductive loads such as motors and transformers can cause a significant drop in power factor. Power factor correction is essential to improve the efficiency of the electrical system, reduce energy costs, and prevent equipment overload. In commercial buildings, air conditioning systems, lighting systems, and other electrical equipment can also contribute to low power factor. Power factor correction can help to reduce energy costs and improve the reliability of the electrical system. In residential settings, power factor is generally less of a concern, as the loads are typically smaller and less inductive. However, certain appliances, such as air conditioners and refrigerators, can have a low power factor. Power factor correction can help to reduce energy consumption and improve the overall efficiency of the home's electrical system. There are standards and regulations governing power factor in different regions. These standards are typically set by regulatory bodies such as the Institute of Electrical and Electronics Engineers or IEE, the International Electrotechnical Commission or IEC, and local utility companies. The standards specify the minimum acceptable power factor for different types of loads and the penalties for violating these standards. The economic benefits of power factor correction include reduced energy costs, increased system capacity, and improved voltage regulation. By improving the power factor, the amount of current flowing through the electrical system is reduced, which leads to lower resistive losses and reduced energy consumption. Power factor correction also frees up capacity in the electrical system, allowing for the addition of new loads without overloading the existing equipment. Improved voltage regulation reduces the risk of equipment malfunction and extends the lifespan of electrical equipment. The environmental impacts of power factor correction are primarily related to reduced energy consumption. By reducing energy consumption, power factor correction helps to conserve natural resources, reduce greenhouse gas emissions, and minimize the environmental impact of electricity generation. Transformerless power factor correction is an advanced technique that eliminates the need for a transformer in the power factor correction circuit. This can result in smaller, lighter, and more efficient power factor correction circuits. However, transformerless power factor correction can be more complex to design and implement, and it may not be suitable for all applications. The dynamic behavior of power factor in power systems refers to the way the power factor changes over time in response to changes in load. The power factor can fluctuate significantly due to variations in the load demand. These fluctuations can affect the stability of the power system and can lead to voltage instability and equipment malfunction. Advanced control techniques, such as adaptive power factor correction, can be used to mitigate the dynamic behavior of power factor and improve the stability of the power system. Modeling and simulating power factor correction circuits using software tools is an important part of the design process. Software tools such as MATLAB Simulink, Power Systems Computer-Aided Design or PSCAD, and Electrical Transient Analyzer Program or ETAP allow our engineers to simulate the behavior of power factor correction circuits under different operating conditions. This helps to optimize the design of the circuits and to ensure that they will meet the required performance specifications. Advanced control techniques can be used for power factor optimization. These techniques include adaptive control, fuzzy logic control, and neural network control. Adaptive control techniques adjust the parameters of the power factor correction circuit in real time to compensate for changes in load. Fuzzy logic control uses fuzzy logic algorithms to control the power factor based on imprecise or incomplete information. Neural network control uses neural networks to learn the relationship between load conditions and optimal power factor correction settings. These advanced control techniques can significantly improve the performance and efficiency of power factor correction circuits. When dealing with power factor, calculations can involve various electrical parameters. Let's consider a scenario where you are tasked with calculating the power factor and correcting it in an industrial facility. Suppose a large motor in a factory draws 480 volts and 50 amps with a measured real power of 15 kilowatts. To calculate the initial power factor, we first calculate the apparent power, which is voltage times current. So 480 volts times 50 amps equals 24,000 volt amps or 24 kilovolt amps. The power factor is then the real power divided by the apparent power, which is 15 kilowatts divided by 24 kilovolt amps, giving us a power factor of 0.625. This indicates a lagging power factor, typical for inductive loads like motors. Now let's say the target power factor is 0.95 to improve efficiency and reduce losses. To achieve this, we need to calculate the amount of reactive power to compensate for. We can use trigonometric relationships to find the initial reactive power. The angle whose cosine is 0.625 is approximately 51.3 degrees. The tangent of this angle is the ratio of reactive power to real power. So, reactive power equals real power times the tangent of 51.3 degrees, which is 15 kilowatts times approximately 1.25, giving us 18.75 kiloVars. Similarly, for the target power factor of 0.95, the angle whose cosine is 0.95 is approximately 18.2 degrees. The tangent of this angle is approximately 0.33. So, the target reactive power equals 15 kilowatts times 0.33, which is 4.95 kilovars. The difference between the initial and target reactive power is the amount of reactive power that needs to be compensated for, which is 18.75 kilovars minus 4.95 kilovars, equaling 13.8 kilovars. To correct the power factor, we need to install capacitors that provide 13.8 kilovars of reactive power. The size of the capacitor can be calculated using the formula capacitance equals reactive power divided by voltage squared times angular frequency. Assuming a frequency of 60 Hz, the angular frequency is 2 times pi times 60, which is approximately 377 radians per second. Plugging in the values, capacitance equals 13,800 Vars divided by 480 volts squared times 377 radians per second. This gives us a capacitance value of approximately 159 microfarads. Therefore, to correct the power factor from 0.625 to 0.95, a capacitor bank of approximately 159 microfarads should be installed in parallel with the motor. Consider a scenario where a commercial building has an overall lagging power factor due to various inductive loads such as air conditioning units, fluorescent lighting, and computer power supplies. The building consumes 200 kilowatts of real power with an apparent power of 250 kilovolt amps, resulting in a power factor of 0.8. The facility manager wants to improve the power factor to 0.95 to reduce energy costs and avoid penalties from the utility company. The initial power factor angle can be found by taking the inverse cosine of 0.8, which is approximately 36.87 degrees. The tangent of this angle is approximately 0.75. Thus, the initial reactive power is 200 kilowatts times 0.75, equaling 150 kilovars. For the target power factor of 0.95, the angle is approximately 18.19 degrees, and the tangent is approximately 0.329. The target reactive power is 200 kilowatts times 0.329, equaling 65.8 kilovars. The required reactive power compensation is the difference between the initial and target reactive power, which is 150 kilovars minus 65.8 kilovars, equaling 84.2 kilovars. To achieve this compensation, a capacitor bank needs to be installed. Assuming the building operates at 208 volts and a frequency of 60 Hz, the capacitance can be calculated using the formula mentioned before. Capacitance equals 84,200 VARs divided by 208 volts squared times 377 radians per second. This gives a capacitance of approximately 5.16 millifarads or 5,160 microfarads. Therefore, to improve the power factor from 0.8 to 0.95 in this commercial building, a capacitor bank of approximately 5.16 millifarads should be installed. These calculations provide a practical understanding of how to assess and correct power factor in different scenarios, highlighting the importance of reactive power compensation for efficient electrical system operation. Different electrical codes may have different requirements. In the United States, the National Electrical Code or NEC provides guidelines and regulations for electrical installations, including power factor correction. While the NEC doesn't explicitly mandate power factor correction for all installations, it addresses issues related to conductor ampacity, voltage drop, and equipment protection, which are indirectly influenced by power factor. For instance, NEC Section 310.15 specifies the requirements for conductor ampacity based on the expected load current. Low power factor increases the current drawn by a load, requiring larger conductors to prevent overheating and voltage drop. Therefore, improving power factor can allow the use of smaller conductors, reducing material costs and improving efficiency. Additionally, NEC Section 430 covers the requirements for motor circuits, which are often significant contributors to low power factor in industrial settings. The NEC requires motor circuits to be protected against overcurrent and short circuits and to have adequate disconnecting means. Power factor correction can reduce the current drawn by motors, improving the performance and lifespan of these protective devices. Many local jurisdictions and utility companies have specific power factor requirements for industrial and commercial customers. These requirements are often aimed at reducing the burden on the electrical grid and improving overall system efficiency. Utility companies may impose penalties for customers with low power factors, typically below 0.85 or 0.9, to incentivize power factor correction. These penalties can take the form of increased energy charges or demand charges. Conversely, utility companies may offer incentives or rebates for customers who implement power factor correction measures. These incentives can help offset the initial cost of installing capacitor banks or other power factor correction equipment, making it more financially attractive for businesses to improve their power factor. In addition to the NEC, other industry standards, such as those published by the Institute of Electrical and Electronics Engineers or IEE, provide guidance on power factor correction techniques and equipment selection. IEE Standard 519, for example, recommends limits for harmonic distortion and voltage distortion in electrical systems, which can be influenced by power factor correction equipment. When implementing power factor correction, it's important to comply with all applicable codes, standards, and regulations. This includes selecting equipment that is listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or UL, and ensuring that the installation is performed by qualified personnel. Regular monitoring and maintenance of power factor correction equipment are also essential to ensure its continued performance and compliance with regulatory requirements. The benefits of maintaining a high power factor extend beyond cost savings and regulatory compliance. Improved power factor can also enhance the reliability and stability of the electrical system, reducing the risk of equipment failure and downtime. In summary, while the NEC may not explicitly mandate power factor correction in all cases, it addresses related issues that are indirectly influenced by power factor. Local jurisdictions and utility companies often have specific power factor requirements and incentives to encourage power factor correction. Compliance with these codes, standards, and regulations is essential for ensuring the safe and efficient operation of electrical systems.